Hello everyone, in this video we are going to talk about stationary points. We also call these points turning points. That are the points where the curve has gradient 0. So at this point, dy over dx equals to 0. In this lesson, we aim to learn how to determine whether a stationary point is a local maximum, local minimum, and the point of inflection. So what are the nature of these points? Now let's look at the nature of these points. Focus on the local maximum. We can see on the left-hand side of the local maximum, the curve has a positive gradient. And then turn to the local maximum, the gradient is 0. And then let's go along. We can see the gradient is negative. Let's continue to move. We can see for this part, the gradient is negative, and then we reach the point of inflection. So at this point, the gradient is 0, and then we continue moving. We can see that the gradient is still negative. So move on. We will reach the local minimum. So at this point, the gradient is 0, and then the gradient becomes to positive. So we can find that at the local maximum point, the left-hand side has a positive gradient and the right-hand side has a negative gradient. So we can fill the table that is positive, here is 0, and then negative. For the local minimum point, the left-hand side is negative, the right-hand side is positive. So from negative gradient to the 0, and then to the positive gradient. For the point of inflection, we have negative gradient, and then becomes to 0, and then is a negative gradient. Also, if we have the curve, looks like that. We can see as we go along with the curve, it has a positive gradient. And then reach the point of inflection, it has the gradient 0. Continue moving, we have the positive gradient. So there are two situations for the point of inflection. So we have positive gradient, and then to 0 gradient, and then to a positive gradient. So we can see in this table, we know that the gradient of the curve on either side of the stationary point. So those are the nature of the local maximum, local minimum, and the point of inflection. Question 1 said that find the coordinates of the stationary point on the curve with equation y equals to x to the power 4 minus 108x. So the question said that you need to find the coordinates of the stationary point. Stationary point means that the point has a gradient, and the point where the curve has the gradient 0. So dy over dx equals to 0. So we need to find the value of the x when dy over dx equals to 0. Now we have the equation y equals to x to the power 4 minus 108x. Then we can differentiate it to get the gradient. That should be dy over dx equals to 4x cubed minus 108. To find stationary point, we need to set up the equation that 4x cubed minus 108 equals to 0. Implies that 4x cubed equals to 108, x cubed equals to 27. So that we have x equals to 3. Now we find x coordinates of this stationary point. Then we can substitute x equals to 3 into the equation to get the y coordinate. Y equals to 3 to the power 4 minus 108 times 3. That equals to negative 243. Thus, the stationary point is 3 minus 243. That is a stationary point. Part B, by considering points on either side of the stationary point, determine whether it is a local maximum, a local minimum, or a point of inflection. Now we consider the gradient on either side of 3 minus 243. So we can set up a table. If x equals to 2.9, x equals to 3.1, and in the middle we have the stationary point that x equals to 3. Now we need to find the gradient at this point. We know that when x equals to 3, the stationary point has a gradient 0. So we feel that this is 0. Now we need to fill the rest of the table. We know that dy over dx equals to 4 times x cubed minus 108. So we substitute the value of x into this function, into the gradient function. So we can write down that 4 times 2.9 cubed minus 108, that equals to negative 10.4 to 3 significant figures by using the calculator. If x equals to 3.1, we have 4 times 3.1 cubed minus 108, that equals to 11.2 to 3 significant figures. So, as a point with the x coordinate equals to 2.9, it has the negative gradient. So stationary point, the gradient is 0. And if x equals to 3.1, the gradient of this point is positive. So we can see that this is a local minimum point. Thus, we've done this question. The second way to determine the nature of a stationary point is that we can use the second derivative. Recap that the second derivative means the rate of change of the gradient function. If we have the positive second derivative, it means that the gradient is increasing. if the second derivative is negative, which means that the gradient is decreasing. And if it is 0, which the gradient is constant, no change. Now, if we have a function f(x) has a stationary point when x equals to 0, then when the second derivative at this point greater than 0, the gradient starts to increase, which means this point is a local minimum. If the second derivative less than 0, the gradient starts to decrease. That is a local maximum. If the second derivative at this point equals to 0, it can be local minimum, local maximum, and a point of inflection. In order to determine the stationary point where the second derivative equals to 0, you need to look at points on either side to determine its nature. Let's see example questions. So, find the coordinates of the stationary points on the curve with equation y equals to x cubed minus 4x squared minus 3x plus 1. Stationary points means that dy over dx equals to 0. So we need to find the value of x when dy over dx equals to 0. Firstly, let's find the gradient function. We have y equals to x cubed minus 4x squared minus 3x plus 1. Thus, the gradient function dy over dx equals to 3x squared minus 8x minus 3. Let dy over dx equals to 0. We have 3x squared minus 8x minus 3 equals to 0. So this equation we can find the x coordinates of the stationary points. We can factorize the left-hand side. We have 3x plus 1 times x minus 3 equals to 0. So we have 2 points. The first step is 3x plus 1 equals to 0. X equals to negative 1 over 3. The second is that x equals to 3. When x equals to negative 1 over 3, y equals to negative 1 over 3 cubed minus 4 times negative thirds squared minus 3 times negative 1 over 3 plus 1 equals to 41 over 27. When x equals to 3, y equals to 3 cubed minus 4 times 3 squared minus 3 times 3 plus 1. That equals to negative 17. So we have two stationary points. The first one is negative 1 over 3, 41 over 27. And the second one is 3, negative 17. So at this point, the gradient equals to 0. Part B said find the second derivative to use it to determine the nature of the stationary points. So firstly, let's write down the equation of the second derivative. We have dy over dx equals to 3x squared minus 8x minus 3. Thus, we have the second derivative equals to 6x minus 8. Two stationary points we have is when x equals to negative 1 over 3. And we substitute this value to the function of the second order derivative. So d2y over dx2 equals to 6 times negative 1 over 3 minus 8 equals to negative 10. That is less than 0, which means this point is the local maximum. We can imagine that the point and the curve looks like that. The second point is that when x equals to 3, at this point, the second derivative equals to 6 times 3 minus 8 equals to 10. That is greater than 0. So the curve past the point looks like that. As the gradient starts to increase. So this is the local minimum. So we have determined the nature of these two stationary points. So in this video, we learned that we can look at the gradient of the curve on either side to determine the nature of the stationary point. And the second approach is that we can use the second derivative to determine the nature of the stationary point. Okay, here is the end of the video. Thank you for watching.